Albert Einstein once asked, if a person such as a mouse looks at the universe, does that change the state of the universe? Whenever Einstein and Niels Bohr met, there was one question they always discussed passionately. Can the properties of an atomic particle be measured without disturbing it? Einstein believed it was possible. At the Solvay Congress in 1930, he wanted to show Bohr how. By means of this apparatus, he claimed it would be possible to register the precise moment at which a single particle of light was emitted from a small opening in the side of the box, and at the same time measure its weight. The physicist Leon Rosenfeld was present at the discussion. He recalls it was quite a shock for Bohr to be faced with this problem. He didn't see the solution at once. During the whole evening, he was extremely unhappy, going from one to the other and trying to persuade them that it couldn't be true. I shall never forget the vision of the two antagonists leaving the club. Einstein, a tall, majestic figure, and Bohr trotting near him, ineffectually pleading that if Einstein's device would work, it would mean the end of physics. But the next morning, Bohr returned triumphantly. Einstein had forgotten to take his own theory of relativity into account. Clocks are affected by gravity. But Einstein wasn't satisfied. He couldn't accept Bohr's claim that it was impossible to measure the properties of an atomic particle without disturbing it. This would mean, he felt, that we shall never be able to obtain a complete picture of physical reality.
Einstein admired Bohr, and Bohr admired Einstein. And you'll recall that Einstein felt that reality exists in effect out there, something independent of us. And the position of Bohr was rather this, that reality is only a word, and we have to learn what the right way is to use that word.
In 1935, Einstein challenged Niels Bohr with another thought experiment. It was to be the last round in the discussion between the two physicists, which they never resolved. This was the experiment which the French physicist Alain Aspect carried out successfully in Paris in 1982. Its aim was to demonstrate the most paradoxical perspectives of Bohr's atomic physics. Even over great distances, atomic particles remain connected to one another.
Bohr, I think, quite early in life had decided that ordinary concepts like space and time simply wouldn't work on the atomic scale. And it was always a little bit unclear what Bohr would replace those concepts by, if anything. But Einstein was very attached to the space-time description and thought that one should try very hard to extend it into the atomic domain. And this was the root of the disagreement between the two men.
In 1905, Einstein, with his theory of relativity, had shaken conventional concepts of time and space. To an observer, if an object is moving at almost the speed of light, namely 186,000 miles per second, time will appear to be passing more slowly. In 1913, Bohr had given a bold explanation of the relationship between light and matter. The atom, the smallest unit of all matter, emits and absorbs energy in the course of so-called quantum jumps. The quantum jump was a transition between two states which physics was quite incapable of describing. It was the development of modern atomic physics, quantum mechanics, in the 1920s that was to separate the true physicists. The Niels Bohr Institute in Copenhagen became one of the most influential centers of physics. Physicists came from all over the world to work here with Bohr. They were faced with conditions in the atomic world that were quite incompatible with traditional thinking. For centuries, light had been described as waves, but in 1905 Einstein had demonstrated that it also had a particle nature. These light particles were called light quanta, or photons. The same thing applied to the atom, whose components were first regarded as being solid particles of matter. But other experiments demonstrated that they could just as well be regarded as waves. How were light and matter to be understood in the face of such contradictory descriptions? In 1927, Niels Bohr compounded the experiences of physicists into an explanation of these problems. To observe atomic particles, you have to use measuring instruments. And this will have its consequences, because observation will inevitably disturb the atomic particle. What we see in reality, Bohr called a phenomenon resulting from an interaction between the measuring apparatus and the atomic particle. When in one experiment the components of the atom behave as particles of matter, and in another as waves, this is due to interactions with different kinds of measuring apparatus. Niels Bohr called this condition for our perception complementarity. Although the particle and the wave cannot be united in an overall picture, we must still accept them as equally necessary for the best possible description. The atom, as it is, free and isolated, thus lies quite beyond our capacity for perception.
Bohr developed a view in which he essentially would say that reality was unknown or unknowable, or even had no meaning in reality by itself. Reality was, except on the large-scale level of ordinary experience, as atomic reality had no meaning. All that we had were phenomena produced in an experiment, and that and the quantum theory deals with the interrelationship of all these phenomena.
Bohr was not a professional philosopher. How much of traditional philosophers he read, one doesn't know. But he was an extremely intelligent man, and he must have thought through some of the issues that professional philosophers had thought through very deeply. And certainly one of the issues that he had thought through considerably, with some help, I think, from reading, was the Kantian issue of the status of a thing in itself. The thing as it really is, quite apart from any human perception of it. Bohr, like Kant, was very suspicious that one can say anything significant, intelligent, controllable about the thing in itself. He once said that physics or science in general is not about nature, it's about nature exposed to our observation. And that is very Kantian.
This was more than Einstein could accept. It might be necessary for the time being to describe the atom by the contradictory terms particle and wave, but eventually a complete understanding of the atomic world must be possible. He was always reminded of the harmony that reveals itself in all being. To the very end, he worked on describing the universe in a unified theory. He once compared it to solving a well-designed crossword puzzle. You may propose any word as the solution, but there is only one word which really solves the puzzle in all its forms. It is an outcome of faith that nature, as she is perceptible to our five senses, takes the character of such a well-formulated puzzle. The successes reaped up to now by science do, it is true, give a certain encouragement for this faith. Einstein disapproved of Bohr's view that our knowledge of reality in physics consists of phenomena resulting from interactions with a measuring instrument. Einstein wanted to understand physical reality as it exists independently of our observation. he made his point by telling Bohr that God does not play dice. Bohr retorted that Einstein should stop telling God what to do.
In Einstein's talk that he gave before my relativity seminar, the last talk that he ever gave in his life, in it, he spoke about relativity and what it meant to him, how he had come to it. But then he went on to speak of the quantum physics. And there he spoke of his discomfort with the idea that the choice by the observer or the observing equipment has anything to do with the matter. He put it this way as he paced up and down before the black table. If a person, such as a mouse, looks at the universe, does that change the state of the universe? His vivid way to make it seem preposterous.
In 1935, Einstein presented Bohr with a final challenge. This thought experiment was only ultimately clarified many years later by the French physicist Alain Aspect. In an article which he wrote together with two other physicists, Podolsky and Rosen, in the Physical Review, Einstein posed the question, does quantum mechanics provide a complete description of physical reality? Einstein wanted to demonstrate that it was possible to perceive a part of physical reality without its being disturbed by the measuring apparatus. The experiment allowed two particles with common properties to be emitted from the same source. It should then be possible, by measuring one of these particles, to obtain knowledge about the other particle without disturbing this other particle in any way. But the real purpose of the thought experiment was to demonstrate that Bohr's atomic physics contained certain absurdities. In this same example, the consequence of quantum mechanics would be that a measurement of one particle would exercise an influence on the other. In fact, only then would the properties of the two particles be determined at all. In principle, the other particle could cross enormous distances in time and space. Bohr's atomic physics therefore implied a paradox. It conflicted entirely with Einstein's picture of the world. No event could create an effect simultaneously somewhere else in space. In Einstein's view, the different parts of the universe were only connected with each other through effects or signals that could not be transmitted faster than the speed of light, and whose origins could always be traced back to a cause in an individual part. Einstein claimed that all events have a local cause.
Local causality is the idea that what we do here in this region of space has no immediate effects in a distant region of space. In fact, it has no effects until a lapse of time which is limited by the velocity of light. Now, this was an important principle in Einstein's relativity. There's one to which he was strongly attached, and it is one which is not present in quantum mechanics, because quantum mechanics doesn't give you this analysis of the world into different space-time regions. The whole thing is treated as a unified thing, and Bohr insisted very strongly on the indivisible nature of quantum phenomena. If two particles had interacted and separated, they were still one system. And it was wrong from Bohr's point of view to try to think of how to divide it up into something happening in this space-time region and something happening in that space-time region.
At the Institute in Copenhagen, Einstein's article came as a great surprise to Bohr. The physicist Leon Rosenfeld was working with Bohr at the time. As soon as Bohr had heard my report of Einstein's argument, everything else was abandoned. We had to clear up such a misunderstanding at once. In great excitement, Bohr immediately started dictating to me the outline of such a reply. Very soon, however, he became hesitant. No, this won't do. We must try all over again. We must make it quite clear. So it went on for a while with growing wonder at the unexpected subtlety of the argument. Eventually he broke off with the familiar remark that he must sleep on it. The next morning he at once took up the dictation again, and I was struck by the change in the tone of the sentences. There was no trace in them of the previous day's sharp expressions of dissent. As I pointed out to him that he seemed to take a milder view of the case, he smiled. That's a sign, he said, that we are beginning to understand the problem. In his reply, Bohr emphasized that our ideas and concepts are rooted in our everyday experience. We are therefore incapable of forming a picture of the atomic world. Strangely enough, Bohr refrained from refuting the paradoxical consequences of quantum mechanics as described by Einstein. He believed that the two particles should be understood as a unified system. We have to do with a wholeness that is completely foreign to classical physics, he said.
Bohr once said that clarity and truth are incompatible variables or complementary variables, and perhaps that both answer is true, but I am sure that it is not clear. Well, roughly speaking, as far as I understand it, Bohr said that you cannot consider separately the various pieces of an experiment. In Einstein, Podolsky, and Rosen reasoning, they were considering on one hand the system on which bear the measurements, and on the other hand the measuring apparatus. And Bohr said you have to consider everything as a whole, the system that is measured and the system that you measured. Everything is a whole, and if you are not allowed to consider different parts in the experiment, then the Einstein reasoning no longer holds.
There is a famous sentence, something like that. Although there is no influence of the one experiment on the other, there is a change in the very conditions for the possibilities of knowledge. There is a very well-turned sentence which I believe Bohr took a great deal of trouble in formulating, and whose meaning is just absolutely obscure to me. So what I get out of Bohr's reply, and certainly what Einstein got out of Bohr's reply, was simply the insistence that we have no right to a picture of the atomic world.
It was John Bell who in 1965 derived a theorem which proved that Einstein's thought experiment could be carried out in practice. John Bell became the judge of the controversy.
At the time of Einstein and Bohr, it was just a theoretical discussion. You could endorse either Einstein's position or Bohr's position, and it was just a matter of taste. And then there was the great discovery by John Bell in 1965 that it is not only a matter of taste, because according to the position that you have, at a certain point, you have predictions which are not the same. If you follow Einstein, you have a certain type of predictions. That is to say, you have results in agreement with what is called Bell's inequalities. And if you follow Bohr's position, you have another type of prediction which are in contradiction, in opposition with Bell's inequalities. And this was a good reason for doing the experiment.
In 1982, in Paris, Einstein's thought experiment was put into practice. Aspect's experiment involved the polarization of photons. Polarization means that light oscillates in specific planes. A polarization filter will only permit light to pass if it oscillates in a specific plane. In Aspect's experiment, lasers irradiate the element calcium. This causes two photons to be emitted from the same calcium atom simultaneously. Measuring instruments on both sides register the photons. In order to determine the polarizations, polarization filters are inserted. Sometimes the photons pass through. At other times, they are stopped by the polarization filters. The measuring instruments register the photons that pass through. The polarization filters can be turned so that it is possible to register photons of other polarization directions. Aspect compared the polarizations of the two photons and observed a correlation. If the polarization filters were set identically, both photons would always either pass through or be stopped. How could this correlation between the two photons be explained? One possibility was that the polarizations of the two photons might be predetermined from the very moment of emission. This would be entirely in the spirit of Einstein.
A reasonable picture in the mind of Einstein was to admit that at the very beginning the two particles have something in common. They bring with them a common property until the last moment. And at the last moment, when you make the measurement, the result of the measurement is due to this property. So you have a property at the beginning, then each particle brings a property, and then the result of the measurement depends on the property, and there is nothing spooky in this picture. This was a picture by Einstein.
In order to find out whether the polarizations of the two photons could be predetermined, the respective settings of the polarization filters would have to be different. Then one might expect a certain limit to the number of pairs of photons that ought to pass through. This limit was known as Bell's inequality. Aspect performed measurements of many thousands of pairs of photons. A counter connected to the measuring instruments recorded when both photons passed through. The setting of the polarization filters was varied in many directions. However, the results of the measurements showed that it was impossible for the photons to have predetermined polarizations at the moment of emission.
If you believe that the property belongs to the photon from the beginning, from the emission to the source, then the result of measurements must obey to a certain inequality that you call Bell's inequalities. And we have found experimental results violating Bell's inequalities. So we are compelled to reject the idea that the polarization of the photon was already existing just after the emission.
The experiment thus pointed to the peculiar fact that the photons chose a common polarization at some moment or other after their emission from the calcium atom. Could it be conceivable that an unknown signal would have time to inform the photons about the setting of the polarization filters? Einstein's theory of relativity insists that no signal can be transmitted faster than the speed of light, namely 186,000 miles per second. Aspect was obliged to improve his experiment.
You have to change something on this side fast enough in order to change it before any information has been transmitted to the other side of the experiment. There are 12 meters between both ends of the experiment. It takes 40 nanoseconds for the light to travel from this end to the other end. If I change something in less than 40 nanoseconds, then what I do here will not be known by the apparatus on the other side.
On both sides, Aspect now placed two polarization filters with different polarization directions. And in between them, a specially developed optical switch. The optical switch now sends the photon out to one of the two polarization filters. It cannot know to which. The switch changes direction in a millionth of a second. Everything now took place so fast that even an unknown signal traveling at the speed of light would not have time to inform the other photons.
And when you switch here, this optical switch, from the up to the down direction, everything is equivalent to a single polarizer that you turn from the first direction to the second direction. And all this system is equivalent to a single polarizer that you switch very fast within a few nanoseconds from one direction to another direction. This was a trick used for the experiment.
Once again, Aspect made measurements of thousands of pairs of photons. And he was still able to observe a correlation between the two photons. Either both photons would pass through, or they would both be stopped. This decisive version of the experiment established the paradoxical fact that the photons did not decide on the same polarization until the actual moment of measurement, when they're 12 meters apart, a distance that could have been infinitely greater.
We have found results in perfect agreement with the quantum mechanical predictions. There is absolutely no deviation, and quantum mechanics predicts that this correlation will not change when you go very far apart, even if you go to cosmological distances.
The conclusion of the experiment supported Niels Bohr's contention that the properties of the two particles are not determined until the moment of measurement. This was what Einstein in 1935 found absurd and described as spooky actions at a distance.
Brutal fact is that Aspect's experiment confirms quantum mechanics, and it confirms it in this very peculiar situation. So that I'm obliged to admit that the quantum correlations exist in the world, and if we are to explain them and not just accept them as given, if we are to explain them, we are obliged to invoke something like actions going faster than light from one place to another. Now that in itself you could digest, but there is this very curious feature that although I'm obliged to invoke such actions to explain the quantum correlations, I'm also obliged to admit that there's nothing I can do with these. I cannot use these long-range effects to send messages faster than light, for example. That also emerges from the quantum formalism. So there's this strange dichotomy between what I can do. Human actions are limited by locality. The causality is local. And the kind of thing I need to give an explanation of peculiar quantum phenomena. It's as if somebody was playing a trick on us. It's as if behind the scenes. Imagine, for example, that you have a railway system. We know that the trains cannot go faster than light, but you might, by studying the timetable very carefully, discover that during the night, trains have to be returned to their starting point faster than light. So behind the scenes, extraordinary things are happening which we cannot use personally. And this is a dilemma. I don't think we have a good way of looking at it.
One of the great peculiarities of quantum mechanics, which Schrödinger already realized in 1926, is that in many situations, two distinct physical systems are characterized by a single state, in such a way that if you try to characterize the state of one part, you must refer to the state of the other part. And if you refer to the state of the second part, you must refer to the state of the first. The two systems, as he put it, are entangled. Now, the various advocates of hidden variable theories wanted to interpret this entanglement in terms of human knowledge. They wanted to say there is no real entanglement of the states of these systems. The entanglement is of our knowledge. If we know something about System 1, we can infer something about System 2 and vice versa. One of the most fundamental, if not the most fundamental results of aspect is to say that this entanglement is objective. It's not merely a matter of human knowledge. That nature itself is constituted in such a way that systems, two well-distinguished systems, can have entangled states.
The ordinary worldview is one which we could call mechanism, in which the world is made of separate entities, such as particles, which when they are far apart do not greatly affect each other. That is, they may interact strongly when they're close together. Now, if they do affect each other far apart, you could always explain it by a field such as light, which would carry the effect through space. Now, in this case, we have a connection between these particles which is not carried by any such field, and which may go over long distances. Now, this suggests that the world is not made of separate elements, but rather, if you follow it through, that the world is one whole, unbroken whole. That is, it is possible to have all these things connected together over very long distances into a whole which is not analyzable into parts. Both quantum mechanics and relativity suggest the world is not made of separate elements, but it is unbroken whole in flowing movement. The image of that would be a flowing water. If you had vortices in this water, each vortex may be thought of as separate, but really they merge together. There's never any separation. Right? Now, that is one image, and but this experiment of aspect deals with a still more fundamental wholeness, in the sense that things which are far apart are still related deeply, or may be related deeply, in a way which is quite foreign to classical or mechanistic concepts.
But of course, we can ask ourselves whether Einstein's, Podolsky's, Rosen's, and our own, I would almost say, prejudices, which we have about something having to exist, whether we are really satisfied with this, whether we don't still feel that there is something unsatisfactory from a philosophical standpoint. And so we probably do have a prejudice. And I think Bohr would stress the need to regard the situation as a whole and just remain satisfied with quantum mechanics. But Einstein and the rest of us, and in his heart even Bohr himself, suffer from the prejudice that something has to exist. But then we have learned that we should not have such prejudices. It would be like saying, but we can see that the world is flat despite the fact that we have flown round it. But then we have to discard prejudices of this kind to the effect that something has to exist. I think that's what we must do. We can't prescribe how the world should exist on the basis of our prejudices, but accept what nature teaches us. And nature agrees with quantum mechanics.
As Bohr's position could be summarized today, no elementary quantum phenomenon is a phenomenon until it has been brought to a close by an irreversible act of amplification, like the triggering of a Geiger counter, or the click of a photodetector, or the blackening of a grain of photographic emulsion. Until that happens, this phenomenon to be is not yet a phenomenon. It's like a great smoky dragon. It has no position in space, no location in time. You know only the tail, where the quantum or the photon or the electron or whatever you're dealing with entered the equipment. But until the dragon has bit with its teeth one counter or the other, you have no right to speak of where it is or what it's doing. It's the strangest thing in this strange world, this elementary quantum phenomenon of Niels Bohr. And yet, of all the things we've learned, it is the central point and lesson of 20th century physics, so that the tale that gave rise to that dragon, that great smoky dragon, gave us only a smoky dragon. It did not become a definite phenomenon until at the end we, by our choice of observing device, made it bite equipment, give us a phenomenon, produce a count, or blacken a grain of emulsion. So in this sense, we have become participators in the construction of the universe. We have no right to say that the past exists independent of the act of observation. The past exists only insofar as it's present in the records of the here and the now.
Well, I can't say that I have no interpretation, but the important point, the important lesson of this kind of experiment is that it truly emphasizes what we already knew, but it emphasizes the fact that when you have a situation that can be described only by quantum mechanics, then you can have no picture that you build from the usual world. I mean from the world that you know at your scale. The world at an atomic scale must be described by quantum mechanics, and if you want to use the usual picture, then you have strange models. So you have only two choices. Either you decide that you don't need any picture, you just write equations, and then everything is okay. And it's quantum mechanics. You just write equations, you make prediction, you make the measurements are in agreement with the prediction. That's enough. If you want a picture, the only picture that you can build comes from your usual world. And then, when you want to use this picture for the atomic world, then there is always something strange in the picture. That is all that I can say.
When Niels Bohr was awarded the Order of the Elephant, he chose the Chinese yin-yang symbol for his coat of arms. And his motto reads, "Opposites are complementary."
A few hours before Bohr died, he remarked, "They," and he was speaking of certain philosophers, "do not understand that we can learn something important from nature and something of very great importance." And he went on to say they did not appreciate that this description, and he meant the complementary description of nature, where we have a part through the very asking of our questions in bringing about that which happens. This complementary description of nature is the only possible description of nature.
For a parallel to the lesson of atomic physics, Niels Bohr wrote, "We must look towards thinkers like Buddha and Lao Tse, who tried to harmonize our position, both as spectators and as actors, in the great drama of existence."